Welcome everyone to today's Veolia Water Tech Talk Plug and Play Phosphorus Removal. My name is TJ Willits and I'll be your moderator for today's event. And we just have a few housekeeping slides to go over. First would be that in terms of the audio portion of the presentation, you should be hearing me speak now. There are two ways to listen to the presentation. You could either listen in through your computer speakers or your headphones. If you have issues with that, you could switch over to the phone call method and use a dial-in number and listen to the presentation that way. Everyone's microphones are muted. However, the presentation is actually being recorded and you'll be sent a recording that you could watch on demand about a day or two after the webinar closes out today. Now, despite everyone's microphones being muted, we still wanted to make this as interactive as possible. And if you look on the right side of your screen, you'll see a question panel. Anytime throughout the presentation, just go ahead and type that question that you have in there, and we'll try to get to as many as possible after the main portion of today's presentation. Now, this webinar is part of a greater series called the Veolia Water Tech Talks. We're wrapping up our spring semester for the Tech Talks, but check out our website. And we'll be listing new and future webinars there as they get announced. And outside of the live presentations that we do, the webinars that we do, we also have 50+ webinars available on demand on our website that you could go ahead and watch at your leisure. And there's a variety of water and wastewater treatment topics there that you could browse, again, at our website, veoliawatertech.com. Now, if you're joining us here for the live presentation, you will receive a PDF participation certificate about a day or so after the webinar. So be on the lookout in your email, check your spam folder, otherwise for that PDF certificate. And after the webinar, you'll be taken to a survey about today's presentation. It's a really short survey, maybe 20 seconds to fill that out. But if you do take the time to fill that out, you'll be entered into a drawing for a $25 Amazon gift card. Your feedback will help us improve these events as we go forward. And also, it gives you a chance to list some topics that you might want to learn about in future broadcasts. Now, a little bit about Veolia Water Technologies. We are a leading water and wastewater treatment company, and we provide customers with a variety of capabilities over the course of projects, specific technologies and equipment, and of course, servicing those projects and technologies with a wide range of services. We support pretty much every industry, industrial, municipal. You can see a lot of those listed there with their water and wastewater treatment needs. And now we will transition to the main technical portion of today's presentation. With us here today is Mark Stewart. Mark has over 20 years of water treatment experience. He started in 1999 at International Paper, where he was exposed to the water and wastewater treatment. And he joined Veolia in 2004 as a project manager, and he eventually became the product manager for Hydrotech Filtration at the office in Cary, North Carolina, focusing on the municipal market within the US. And in June, just recently, he became the regional sales manager for Hydrotech, responsible for managing sales and marketing and commercialization activities in North and South America for both municipal and industrial clients. We're really fortunate to have him and all his experience that he's about to share with us for today's presentation. So I'm going to hand over the webinar over to Mark. Mark, are you with us?
I am. Can you hear me?
Hello? Yes, Mark, good to go.
Excellent. All right, thank you, TJ. So I'm excited to be sharing with you here about phosphorus removal. And we'll just start with a brief agenda. We'll talk through these items here. Of course, starting with why is this even important? You probably know that already if you're joining, but I think it's helpful to kind of lay the groundwork. We will share about kind of a broad overview of available phosphorus removal technologies. Then we'll get into the detailed technology we want to share with you today, what we call plug and play. a brand name we call NutriPack, which combines disc or drum filtration with coagulation and flocculation to precipitate phosphorus into a solid form that can be removed by those filters. And we'll talk about those benefits, and we'll share with you some real-world sites that have been able to implement this successfully, those case studies. Finally, we'll sum up with a few tips on how we can coordinate with you and help you get started if you have a phosphorus removal project you want to look at. And then we'll have some time for questions and answers at the end. So as I said, we'll start with a little bit of groundwork. Why is phosphorus removal important? And it really comes down to our environment and the impact that nutrients can have when discharged into the waterways. So when these nutrients, nitrogen and phosphorus-based compounds get into the waterways, really results in the algae that is present in those waterways using that and growing excessively. This is called eutrophication. And when they do that, then they're uptaking the oxygen in the water, and that has a negative impact on the aquatic life. So many places will see fish kills and other damage to the ecosystem there, which is not a good scenario. It's also can be quite unsightly from a tourism and swimming type scenario. So definitely things that the governments and the people have decided that this is not something we want to continue. And in terms of sources of where this comes from wastewater, it can be residual nutrients from the processes that a particular plant may have. Could be cleaning chemicals. Many of those use phosphate type compounds in their chemicals and detergents, and then nutrients inherent to just organics. So farming and even municipal wastewater carries with it nutrients laden in that. In 1972, the U.S. had the Clean Water Act passed, which really began a focus on protecting and trying to restore these waterways. And you can see there throughout the 2000s following that, EPA publishing nutrient criteria, progress reports on where that stood in 2008. In 2011, reiterating the need for states to really develop the nutrient standards they needed to protect the waterways within their boundaries. And 2016, again, a renewed call to action to reduce nutrient pollution. And you can see here on the left a photo of Chesapeake Bay in eastern United States. So as a result of this, we are seeing and have seen over the last several years increasingly strict both nitrogen and phosphorus limits in these permit renewals. Municipalities are really shifting that burden onto, as they can, their clients that are sending them wastewater to the treatment plants. And you can see here just a little snippet from this EPA memorandum. Nutrient pollution remains one of the greatest challenges to our nation's water quality and presents a growing threat to public health and local economies, contributing to toxic, harmful algal blooms, contamination of drinking water sources, and costly impacts on recreation, tourism, and fisheries. We have many attendees here, I believe, from Canada as well today, and very similar scenario, although regulation for Canada is really at the provincial level. But nonetheless, an evaluation is really made at the local level with these receiving water bodies to determine how sensitive they are and what types of impact the wastewater could be having coming in, and what the limits need to be as a result to try to limit and improve those impacts and improve the water body. So as an example, in British Columbia, while sea outfalls really don't have any requirements overall, the province has a 1 milligram per liter total phosphorus limitation, but then sensitive water bodies such as Okanagan Lake can have more stringent limits, as we see here with a total phosphorus of 0.25 milligrams per liter. And then again in Alberta is another example, global regulation within the province of total phosphorus less than 1 milligrams per liter, but it can be a case-by-case consideration on whether a receiving body may need to have more stringent limitations for those ones that may be discharging into that water body. Now, what are some key applications that could be affected by this? Well, it really is a wide spectrum, as you can see here, from dairy, food and bev processing, meat packing, fertilizer producers, metal finishing, where they can use phosphate type chemicals in that process, and of course municipal wastewater, as we mentioned earlier. So this certainly doesn't cover all of those industries, because at the end of the day, if you have a limitation that needs to be met, then you're impacted here by this and the need to remove the phosphorus. So we're going to go into the discussion of technologies, and from sort of a big overview perspective, many plants will have many stages of treatment. You could have primary treatment to remove solids at the first stages of the plant. Many times these stages, if the plant has a nutrient removal, will implement chemical dosing to enhance their primary treatment in order to start to remove the phosphorus. Secondary treatment is another key component, where you can have typically biological treatment to help with removing phosphorus. That's very effective. The technology that we're going to share specifically about today would be usually considered the tertiary or polishing step, to really get to the low levels of phosphorus removal and effluent limitations that need to be met. So when we talk about phosphorus or nutrient removal, today we're really, again, focusing on phosphorus. There's two main kind of categories or methods. One is biologically. And here we're talking about systems that are activated sludge, or sequencing batch reactors, MBBR, membrane bioreactors. All of these are using biological treatment system with the bacteria, using the nutrients and uptaking them in order to process them and remove them through the flock, and being disposed of through the sludge, the biological sludge from those processes. Alternatively, you have physically or chemically those methods of removal. And here, physically, we're talking about clarification, so settling, and that could be either traditional clarification with large retention times and a settling mechanism to allow the solids to settle, or high rate clarifiers, where they use some methods to speed up that process and get the solids to settle faster. Could be flotation, could be filtration, from media filters to actual cloth filters. But in any case, many times the phosphorus is not only in a solid form, it can be dissolved in the water. And when it's dissolved, then a chemical step will be needed in order to turn that into, from a soluble form, to be precipitated with a chemical reaction and turn that into a solid form. And so that's what we're talking about here with coagulation and flocculation. And those steps can be combined with the physical separation in order to increase the phosphorus removal.
Hey, Mark, just to hop in here. We had a question just that popped in. It's probably timely with this slide, but listing biologically and phys-chem, is there a particular reason why you're highlighting phys-chem as an efficient means for P removal?
Yeah, that's a good question. So typically with biological systems, there can be quite a bit of investment in a number of areas, one being footprint, and having the space to implement the biological system, since there are retention times and such to be concerned with. Also, the infrastructure can be quite costly, and the engineering that's involved in designing those systems. So that's not to say the other ones don't have that as well, but many times the physical processes, and particularly compact ones such as we'll be sharing about, have a very small footprint, so they can save in the realm of the space needed, the footprint needed at the plant. They also can be a quick method for implementation, as many of these systems can be pre-engineered, and so they can be very convenient for a plant that may not have all of the infrastructure right now, or may not be having the funds to consider a full biological system upgrade. The physical chemical method could be advantageous to them to get them something that will fit in their facility footprint at a relatively quick time frame, and hopefully a low cost for them.
Thanks, Mark.
Yes. All right, so continuing then with just a very rough, this is, I wouldn't say highly detailed, but from a general standpoint, most sites will be able to use biological treatment for achieving levels down to about 1 milligram per liter of total phosphorus. And having said that, these other methods as well can be used to take higher levels down to that as well. But oftentimes we see that many sites, if they have biological treatment, then will achieve about 1 milligram per liter with clarification and settling or flotation, whatever the process may be they have on site, and maybe with some backup means of coagulation for trimming and meeting their effluent limitations. Typically, to get down to less than that, into the roughly 1 to 0.5 range, a client may need to add another step behind the clarification method. So that could be in this case microscreens as an example of filtration following the clarifiers. That will typically get to about 0.5 milligrams per liter. Getting down to below that into the, say, 0.3, 0.2 range would require an added step ahead of those filters with coagulation and flocculation, and I'll be explaining that as we talk further. And that could typically get you down to as low as below 0.1 milligrams per liter, and then ultra low, less than 0.05, you're talking about quite intensive membrane filtration to achieve those limitations. So we wanted to share here with this webinar specifically the technology we call plug and play phosphorus removal process, and we've termed here as what we call NutriPack. Pack just being focused on the plug and play aspect and being able to package this together. As I said earlier, this is focused around our Hydrotech filtration technology. It's been established for many years, and this is either a disc or drum filter, and I'll share more details of that in a minute. But the exciting thing here is we now have a few categories of where we have pre-engineered coagulation of polymer systems to allow this to be coupled up and to get removal of not only particulate phosphorus, but if you have soluble phosphorus that's in solution and needing to meet low limits, this can be added on and packaged with the system to meet those needs. We'll be sharing the details on this. So first, to talk about the filters, Hydrotech filtration. This is a proven technology. I started selling the disc and drum filters in the 1990s, so over 20 years of experience here with this technology. Continued development to improve that. It's in what we call an inside-out filtration process. I'll explain that further in a minute. It's very effective at solids removal. The media ranges from 1,000 micron in size to 10 micron, and so at those small 10 micron opening cloths, we can get very effective solids removal, up to 95% suspended solids, and this helps us to achieve those high levels of removal when we talk about precipitating phosphorus and trying to get that out of solution. Very small footprint when compared to other filtration technologies, particularly sand filters or in extreme case clarifiers. This will be just a fraction, could be 10% or less of the footprint required to treat the same flow capacity. And then it's very efficient. The filtrate that's used to clean the filters as they collect these solids is the filtered water. So typically does not require an extra water source, just uses the filtrate that's being cleaned through the media. And the filtration is continuous. Some processes oftentimes will need to be taken out of service to clean the process and collect the solids out, but this is a continuous operation, so it doesn't have to be taken offline in order to perform the cleaning of the media and collect the solids. So relatively low power consumption, just has one drive motor and one backwash pump to pump the filtrate for the cleaning. And it's quite easy for operation and maintenance. You can see here it's accessible to operation staff for easy inspection, easy maintenance. How did these work? I mentioned these were what we call inside-out filters. And so to explain that a little bit, you see a couple of diagrams. One here is showing a disc filter sketch and also a drum filter sketch. These both operate in the same format in that the influent comes into the center of a central drum. For the disc filter, from that drum, then the water flows inside to the inside of discs with woven cloth media on each side of those discs. For the drum filter, the water flows inside and then just goes through the cylinder, through the circumference of the cylinder where the media is wrapped around the unit. But in both cases, the effluent flows to the clean side. The solid particulate is captured on the inside of the media, and then the clean filtrate is discharged over an effluent weir. As the solids collect here, the head loss is going to increase through the media, and so the inlet water level rises up. And as it does, that is monitored with instrumentation in order to trigger the backwashing process, which rotates the drum and starts the high pressure spraying in order to clean the particles from the media. Then the solids are collected in a trough that is suspended inside of the drum and flows out of the unit. So you can see the sludge outlet here from the disc filter and the sludge outlet here from the trough on the drum filter. Here's just a couple of photos to show you what a disc filter media panel would look like. So you can see very accessible, easy to inspect, as well as if there needs to be a replacement for any reason, get access and do that. Here you see microscopic photos of a clean media, woven media, and then before backwash with the solids collected. And I want to share a quick video here to just talk through again the process. So here you can see with this computer generated animation, the water coming into the central drum, flowing through the media panels, the solids being collected on the inside. The clean water flows out through the filter panels over a discharge weir. And as solids are collected, the inlet water level rises and triggers the backwash, which will then start the rotation of the drum and the high pressure spray to knock the solids from the inside surface. When the solids are removed inside, they flow into the trough and then gravity flow out of the unit with the backwash water and the sludge being removed. So now I would like to talk about combining that technology with coagulation and flocculation, because this is the key step when we're looking at phosphorus removal that is in solution. So if we talk a little bit about pre-treatment chemistry, if we have influent coming in, we would need to dose some metal salt. This is typically based on either ferric or aluminum-based, iron or aluminum-based metal salts. This will have a chemical reaction with the solubilized phosphorus and produce particles. However, these are typically what we would call unstable particles, not very strong or of adequate size for us to capture them on the filter media. For us, size and strength is critical. And so polymer is typically added. You see the polymer molecule, which when combined with those coagulated particles forms a nice flock, concentrated flock that can be captured on the filter media. And here's just an example site photo. This isn't a drum filter, but you can see really heavy, solid, good flocks there that the filter can then capture and remove. Where does this fit in your treatment process is questions often asked, and so could vary depending on the site and what the needs are, but here's an example of a common location where it would be placed into the system. If the client has existing biological wastewater treatment, such as activated sludge, they may be already dosing coagulant upstream of their clarification step or flotation step. And so this could be envisioned as a tertiary plug-and-play system to put in, depending on the limits, either with coagulant, which would be key if the phosphorus is in solution, or if they're close enough and they feel like that the 10 micron media can remove the particulate, then it may be adequate to just add the filter and achieve their demands before going either to the local municipal treatment works or direct discharge. And here's a diagram just to show what we're talking about of the whole system here. When we're trying to remove soluble phosphorus, we'd have water coming in, dose the metal salt, as we mentioned, typically a mixing stage with either a rapid mixer or a static mixer would be required to provide a thorough, good mixing of the coagulant in the water stream, followed by several minutes with a vertical stage mixer of coagulation, several minutes of retention time. After that, a polymer would be dosed before feeding into a flocculation stage with, again, several minutes of retention time and mixing before going to the filter. At this stage, we've built a good, strong flock of good size and strength that can be well removed, efficiently removed with clean effluent, and the solids can be collected to take to discharge. What we really wanted to focus on here today is that this entire, what you see in this box, can be an integrated system that easily retrofits into an existing wastewater treatment facility. Certainly, all these steps could be acquired individually, but we feel like there's a big advantage. The expertise and experience we've had implementing these systems has allowed us to key in on a few flow ranges and provide pre-engineered systems to make this easy for a facility to implement. Again, that's what we're looking at here with the pre-engineered coagulation and polymer systems. This includes both tanks, mixers, and the dosing. So we typically would use dosing pumps for coagulant and polymer included before feeding to the disc and drum filtration unit. And again, just to highlight what's included in that box, what is being provided here. We're talking about the coagulant mixing. So this is the several minutes of retention time with a mixer. Flock mixing, again, several minutes of retention time, and then going to the filter for discharge. Also included is coagulant dosing pump and polymer dosing system, make down and dosing both. And then finally included with that is our control system with controls strategy PLC logic that we've developed with feedback and feed forward control, which we've been able to prove by using instrumentation to measure the water conditions to get a very effective and I would say dialed in dosage on that. And some of our clients have seen pretty substantial reductions in chemical usage, as well as savings in the volume of sludge produced because of the efficiency of that process. Other options are digitally enabled remote monitoring connected to this system through the cloud. We can also provide advanced deep cleaning. So many times when using chemicals, the filtration will need periodic cleanings, and there are several stages of cleaning that can be provided as add-ons to help with that process. And then finally, chemical and equipment services is something as well that we can offer to help the client as needed. So what are the key benefits of this NutriPack plug-and-play solution? So if we focus on performance, as we've already discussed, when you need to get these low levels of phosphorus, and in some cases, we're seeing locations that are putting permits out with less than 0.1 milligrams per liter of total phosphorus concentrations. It's key to have a solution that can achieve that, and we've proven both with pilot studies, R&D, and now full-scale operating sites that we can achieve that with this technology. That can be done. So 90% reduction of phosphorus. Also the total suspended solids, achieving that high level of suspended solids reduction. I mentioned in the previous slide that we've seen with the PLC logic that we've been able to develop in doing this both in pilots and full scale, that we've seen increased savings for the sludge disposal and production, because you can target, compared to dosing coagulant maybe upstream where it's not as effective. There could be interference from other sources such as carbon-based contaminants and pollution. Here you're dosing it downstream at the tertiary level where you can really focus in on the phosphorus and reduce the coagulant consumption. In some cases, we've seen that reduced by 70%. So optimized chemical usage as well as reduced sludge production. And right now we have this pre-engineered, both with the tanks and the filter, in 3 specific flow ranges. You can see those here, less than 25 cubic meters per hour or 110 gallons per minute. Then from about 25 to 60 cubic meters per hour or 110 to 264 gallons per minute. And then finally from 60 to 120 cubic meters per hour, so from 264 to 528 gallons per minute. You know, one of the key benefits here comes down to footprint. We talked about performance. Now, if we talk about footprint, this really goes in a number of areas, but you know, footprint ends up being, whether it's industrial or municipal, oftentimes associated with dollars. I mean, just as we would sell our house at so many square foot or cost to build it, it's going to be the same here for implementing a solution, a new treatment solution to help meet a limit. And one of the key advantages here is limited footprint. So you can see here, compared to this example facility in their existing wastewater treatment plant, the solution to add on the NutriPack and provide them with the phosphorus removal they need is just a fraction of that footprint, in this case within 2 by 5 meter footprint. Final benefits I wanted to highlight was implementation benefits. So again, these 3 flow ranges we're talking about are pre-engineered. You can package this up with the tanks, the filter, the controls, the chemical dosing, all pre-engineered, ready to go. This is saving the client in time as well as money in not having to research this and either have a consulting engineer chase this or potentially themselves have to try to work with several different integrators, but having one integrator for this solution. With that would come our in-factory mechanical and process checks to make sure that it's well functioning. Can be limited civil works, either to put this on grade, put it in a small building, or we even can containerize it to ship in a container to put right on at the site. And a relatively quick startup and commissioning, as opposed to some processes that may have long startup times. This really is, once it's piped and electrically connected, it's ready to be put into service. And finally, a relatively low impact on operations staff, since it's simple to operate, simple to maintain. We thought it would be helpful just to wrap up with a few examples of how the technology has been able to help some clients be successful. This is more holistically looking at full-scale implementation from large sites, as you can see, in some cases up to 30 million gallons per day or almost 5,000 cubic meters per hour, here as you can see, to very small plants, down at 70 cubic meters per hour, about 400,000 gallons per day. And key here is you can see a range of, each client has different needs, some of them not as stringent, but here with these ones we have listed, many of them targeting even down as low as 0.075 milligrams per liter. And these clients, many of them are municipal, but also industrial as well. So this is a mix of locations, both municipally and industrial, for using this technology for their phosphorus removal. Some specific locations. This is a location in Pennsylvania. It's a chocolate producer. Many of you would well know the name. They had an overall need to provide a upgrade and replacement of their outdated wastewater facility. As well, they wanted to proof themselves, I guess we would call it future proofing, prepare for the future and what the limitations could be. So for their design basis specific to phosphorus, they're looking at an influent of around 7 was the design basis, and a need to meet an effluent discharge of less than 2. You can see in this case, they have a number of biological stages. They have a DAF for the flotation to remove solids, but they also had a need to then implement, as well as a polishing step, the Hydrotech disc filter, and prior to that did have a flocculation stage as well in order to catch and polish those final particles of phosphorus and get the limits they needed. And here's a graph just to show some results that we've been able to gather. So these levels of total P are to the overall facility, and you can see that while the design basis was targeted at about 7 was the target, 6.9 was the design basis, so about 7 milligrams per liter. You can actually see that in many cases it was even above 10 and up to 15 milligrams per liter. But despite that, able to meet the overall average target of less than 2 for them in the final effluent, and the disc filter being a key component to that treatment system. Another case study here was a dairy client. It's cheese products that they again needed to implement a process to treat their wastewater prior to discharge. Key drivers here was really the discharge regulations and being able to keep this business running and meet their production goals. Their results, their influent has averaged about 3 milligrams per liter. They are up and running and are consistently meeting their target, which they're stringent for them. Their limitation was less than 0.7, and they are able to achieve that. This site has, again, the chemical pretreatment tanks upstream with coagulation and flocculation, followed by the filtration system. Then I also wanted to mention this municipal case. This case was an existing wastewater treatment plant. They had a target of less than 0.075 milligrams per liter of total phosphorus to be met by 2024. They were not able to do that with their current wastewater treatment plant. So of course, regulatory compliance was a key driver for them, but another driver for them was to try to be compact and stay within the existing footprint of the facility. So the Hydrotech filters were a key part of that because they were able to be placed inside the existing infrastructure. These basins that you see that the filters are installed in were prior sand filters. So this was a big advantage to this site to be compact and to fit into their existing footprint. And here's some data when this was started up at this location. You can see once they started the chemical dose, they were averaging about 0.2 milligrams per liter on the inlet to the filter. This is not the plant influent, this is the influent to the filter system, or prior to the coagulation and flocculation tanks actually. And once they started the chemical dosing, they were able to drop that right below. So very efficient and effective, keeping that below their effluent TP criteria 0.075 and actually averaging just under 0.05 milligrams per liter of effluent phosphorus. And there's some photos there. You can see the flocks. This is in the upper photo. Top photo is just a beaker collected through a glass beaker. You can see the well-formed flocks, and the lower one is in the zone, flocculation zone, prior to being fed to the filter. So how would we get started if you have a need and are interested? A key thing would be to know what the goals are. What do you need to achieve? So of course, new and updated permits or regulations is a starting point. Knowing what your current system is doing and the performance it's getting. So data collection, as we're showing there, is a key part of that in order to establish where are we at and where do we need to get to. If that's not on hand, then maybe we can use some production numbers or other methods to estimate and try to determine what the current situation is and what our system can achieve in order to get to where the site needs to go. And another thing, maybe that's not the current scenario. Maybe you don't have the existing limitations, but maybe you're looking to, as we said, future-proof or prepare for the long-term wastewater planning. That could be another scenario where you may want to reach out to us and say, I don't have an immediate need, but I do want to be prepared in case this comes down the road several years, because I'm hearing that in our locality that this is a concern. So that could be a reason to get started and to reach out to us. All right, so we have reached the time for question and answer and wrap up.
Mark, thanks so much for sharing all that experience and those cases and introducing this particular technology. I just want to remind everyone, on the right side of your screen is that question panel or that question chat box. Go ahead and enter a question if you have that. We have a handful already that are in the queue here that we'll try to get to. But go ahead and enter that in, and we'll try to answer that question at today's live broadcast. A lot of questions about the media or the microscreens. So maybe we'll do a couple of those first, Mark, if that's okay.
Absolutely.
So just a general question here. Is there any concerns about blinding or plugging of the microscreens for that smaller pore size, that 10 micron filtration media size? Can you comment about after you dose with chemicals, if there is that potential where it would actually inhibit the filtration with those filters being blinded?
Yes, that's an excellent question. And I'll answer it kind of in two stages. One, for the short term, the backwashing that uses the filtrate is very effective and typically will clean very well, to continue the filter in operation. But as you add chemicals such as these coagulants, they will precipitate over time. So it's typically not a rapid thing, but say over weeks and months, there can be a precipitation. So basically these compounds can crystallize and adhere themselves to the fibers of the media. And so, as we had said earlier, we do have systems that would need to be included and are a critical part of that in order to restore the media. And we've shown that using these chemicals, we can restore the media. So it's really a maintenance regimen that needs to be followed, and very straightforward, semi-automatic, as we said. So there's some makeup and things that the operators would need to do, but once they've done that, hook up the system, push the button, and it's automated in terms of the cleaning process to restore the media and get it back to full capacity.
Yeah, great. Thanks, Mark. An interesting question here. Can the microscreen filters be used after a skidded DAF for enhanced separation? So can you comment if that would work with potentially that process there?
Yeah, absolutely. We do have installations downstream of DAF, so we'd need to get into a little bit more of the specifics about what the target desire is to achieve, but it definitely can be installed. And we do have installations using filters downstream of DAF for improved polishing.
Great. This is sort of an influent question here. What is the max suspended solids concentration, including the phosphorus precipitate, that's acceptable for the inlet going into the Discharge drum filters?
Yeah, that's an excellent question. I would say generally most sites are probably in the 20 to 50 milligram per liter range, but can be higher. It really all depends. I hesitate to give an actual, hey, it's this value, whether it's 100, 200 or whatever, because really it comes down to trying to size the unit appropriately for the specific concentrations that the client has. So hopefully that gives enough just to kind of give you an idea. I would say, again, most sites are probably, 20, 30, 40 milligrams per liter suspended solids peak values usually. But there can be cases where that could be higher, and particularly, it's going to depend on once you add the chemical, how high that's going to need to get in order to get the phosphorus out as well. So those are some general values, but if we had specific cases, we could look at that and then hopefully just size the filter accordingly to still be an economic fit for that particular site.
Going back to the filter media there, can you talk a little bit about the various ranges of pore sizes that you offer, and then go and talk about, well, what size do you select for what type of application?
That's a great question. Yeah, so as mentioned earlier, they range from at the highest end 1,000 micron, which is about a 1 millimeter opening, down to 10 micron, being the smallest pore size. And when we're talking about tertiary polishing, as most of the discussion has been here, we're typically looking at 10 to 20 micron is usually used for that, because we do need to remove pretty fine particulate. Now, it could be that in a case a client has, say, a higher level treatment need with maybe more solids and they don't need to get as stringent on the effluent. In those cases, we basically look at our experience and look at whether a higher micron size, 50, 100, 200, 300, would be appropriate. But again, typically with these low-level phosphorus applications, we're looking at the smallest, either 10 or 20 micron pore size for that filtration.
Great. A really specific question on the list of the case studies someone asked there. It says, do you know what the media pore size is used at that 31 MGD plant in Wisconsin? Looks like that is the Brookfield plant in Wisconsin. And then, do you know what kind of chemicals are used in this particular application? I don't know if that's a tall challenge or not for you, Mark.
I'm pretty familiar with that site, so I'm almost positive that the pore size is 10 micron. I honestly do not remember whether they are using ferric or alum-based coagulant. I want to say I think it's ferric, either ferric chloride or maybe ferric sulfate, but I could be wrong there. But I could definitely find out and try to get back with that person if they're interested, but that's my best memory off the top of my head.
Great. Another question that just came in here is, in your experience, Mark, is a polymer dosing even necessary to achieve P removal in all the cases? And this also implies the sand filtration, or overdosing coagulants could be an option.
I will say that it depends on the location. There are some locations that have seen some success doing a very fine, very small dosing of coagulant with these types of filters upstream. But the danger there is that if the coagulant does not form a good, strong, solid flock particle, that it will just either go through the filter media or can also really clog and blind and become like a sticky substance on the filter media and cause operational problems that then just has to be either chemically or high pressure cleaned off. So generally, I don't want to say it can't be done, but if you're looking at these low levels where you really need to dose and get low levels, typically what we see is that both a coagulation step and then a polymer addition flocculation step is really needed to get a flock in a form that can be well removed and efficiently removed.
Okay, thanks. While we're talking about dosing, another question, it says, in relation to the NutriPack, our site has to dose coagulant upstream in the clarifier for settability. So does it even make sense to move the coagulant dosing downstream? What's the value of the NutriPack in this particular scenario?
Yeah, that's an excellent question. And I would say it wouldn't necessarily make sense. It would just depend on the site conditions. Many sites will do what they call multi-point coagulant dosing. So they could be dosing at, say, 2 or 3 locations throughout the plant and use that to really trim the facility to hopefully optimize the chemical dosage, get it as low as needed while still meeting their regulations, as well as optimizing the operating conditions. So, if a client here says, well, I need coagulant and I need to dose this much just to, have a good system operation with my clarifier, that makes sense. And maybe it doesn't make sense to remove it then. But if you're not meeting the discharge limits that you need, then it sounds like, yeah, a step could be needed after that in order to dose and get the phosphorus down to the target levels that they need to meet.
Okay. A couple things about cleaning these. Just the first question would be is, can you elaborate on the semi-automatic deep cleaning that was listed as an option for the NutriPack? Long-term fouling is normal within the microscreens. So what does this actually do for the particular client?
Yeah, that's a great question. So we have a couple of different systems, but the typically we will work with the client to implement some type of chemical cleaning regimen, and that, as I said earlier, is maybe on it could be a monthly or quarterly type of cleaning a scheduled operation. The option that I'd mentioned was an additional, what we term, high pressure cleaning system. And this is used when it's included to try to prolong those. So it could, this is basically using an even higher pressure, probably about several times, 5 to 10 times higher pressure than the normal backwashing, to try to remove this foulant, the precipitation. And it does a pretty effective job, not as effective as the chemical, but oftentimes can double the times between needing for chemical cleaning. So could take several, put this into the high pressure cleaning, say once a week, and you could see the need for using the chemicals much less frequency. So that's what the semi-automatic deep clean is referring to, a high pressure cleaning system.
Okay, and then sort of in the same area, this next question talks about, can you talk about the cleaning agents used for these particular Microscreen filters?
Absolutely, yeah. There's a number of different options sites have found effective. Usually, if you're dosing these coagulants, then some type of acidic formulation will need to be used. Ultimately, if you have this chemical precipitation to dissolve those, hydrochloric, say 10 to 15% is usually very effective to do that. So that's used. Generally, some sites, if they have other types of fouling, so it could be, for example, municipal sites often have biofouling, then chlorine type compounds, whether bleach or similar, can be effective to remove that type of fouling. And then we have seen that we've at some sites success with some organic acids, so such as acetic acid, oxalic acid, that have been effective, but it really just depends, and oftentimes that's, if just going to the site and at operation, it's fairly straightforward to be there on site and to help them identify what's effective to clean their particular panels and to keep them up and running.
So this is, we had a handful of questions, Mark, on sludge, so I'm going to sort of batch over to you a couple, but can you talk about sort of the quality of the sludge that comes out, sort of the TSS concentration, talk about what you do with it? Do you dewater it? Do you put the centrate back to the head of the plant for treatment? So maybe you could walk us through sort of your experience of what you see with this particular technology.
Absolutely, fantastic question. I would say that the sludge typically is around 1% total solids concentration. It can be a little bit higher with the chemical addition that we're talking about here, but I'd say that's generally a decent average, and that will depend on how high the concentration is coming in. So if we're at these low levels, that I'd say that's accurate. If you don't have biological treatment, and maybe we have, there are some cases in sites we have that have higher levels of phosphorus that we're dosing, so we don't need to get as low, but maybe we're dosing more chemical than for the lower levels, then maybe those concentrations are a little bit higher, but generally I'd say about 1% average. And in terms of how it's directed, that's another great question. I would say most of the time sites have routed this back upstream if they have existing clarification, either, as was mentioned, to the head of the plant or to a head of the clarifying technology. But it can also be directed to a specific solids removal step if needed, whether that's settling or press or what have you. But very weak, so I would say most of the time it's going back upstream to the plant to be discharged through their normal clarification and solids removal means.
Great. Well, that was just very enlightening, Mark, all of the knowledge and experience and you shared with us here. We got through about, I would say, 90% of our questions. So thank you for everyone that submitted questions. I apologize if we missed your question or didn't answer them exactly, but we really appreciate you still taking the time to submit something. Again, I want to thank first our panelist, Mark Stewart, for all his time and prep in putting this presentation together and sharing this new technology with us. And more importantly, I also want to thank everyone here who spent the time attending this webinar. This is a great opportunity for you to learn a little bit more about what Veolia could do in relation to wastewater treatment. So we really appreciate you spending an hour of your day and spending it with us here at Veolia. So again, thanks for everyone for attending, and we look forward to hosting you in the future on one of our future broadcasts. Take care and have a great day.